This video should in many ways look familiar to those who've seen our videos in the past. But it's meant to communicate an expansion of the research that we're doing on Atlas. So we're not just thinking about how to make the robot move dynamically through its environment like we did in parkour and dance. Now we're starting to put Atlas to work and think about how the robot should be able to perceive and manipulate objects in its environment while maintaining that characteristic high level of performance that we expect from Atlas. In order to do that, the robot has to be able to think about the properties of objects, their shape, their mass properties, and as it's manipulating these objects, the constraints that exist between the robot and the object, the forces that exist, and it has to have a control system that's able to balance what may be competing objectives related to stability or the manipulation task at hand.
My role in the project was working on perception and autonomy. So perception is letting the robot know what it's seeing, and autonomy is letting it choose what it's doing next at a high level, where it's going to go and what it's planning to do. It's all software, so we're writing code that runs onboard Atlas, and it's got computers on board that are processing the camera data so that it can see the objects in front of it. In this video, we're doing a lot of object manipulation, lifting this piece of wood, placing it down, lifting up the tool bag, and eventually jumping and trying to throw it precisely up onto the top platform.
So Atlas has a couple of cameras that we use to see the world around it, and they work not entirely unlike a human eyeballs. So we can see the colors of things around us, and we can get some information about how far they are away. We use that to build models of the environment. So we might know that we're going to be running over a sequence of boxes, and so we see some box-like shapes out in front of us. We decide, oh, those are probably boxes, and we go and we decide to run on top of each of those boxes. And that works really well when the environment looks something like what we're expecting.
The Atlas perception system works with the cameras that are in the head. It has a color camera, and it has another camera called a depth camera. So this uses photons, time of flight, to measure the distances to everything that it can see. We basically are looking for shapes in the environment and other features in the environment that Atlas can use to identify key objects of interest. So I was going to put it down. And then the next thing it's going to go do is go look for the bag. So it's been told the bag is somewhere over here, and now it's got to turn. And right after that turn, the bag is now in the view out here in the distance. And so it's going to start estimating the pose of the bag. You can see there it's found it, and it's sort of thinking about the shape of the bag and how it wants to grasp it like that. And then it comes in, and we get a nice view in the front camera here of the grippers making the grasp around the bag like that.
So the way that we approach this problem is a technique called model predictive control. And the idea is that the robot's control system should be able to think about how its motion is going to evolve in time in a way that respects the physical laws of our universe. So for example, if you're imagining the robot's holding a heavy object while trying to run, or pushing something that weighs on the order of its body mass across the room, carefully considering the forces that exist between the robot and the object and how that might or might not tip the robot over, for example, is really important to success.
So a predictive controller is a way of doing controls by thinking about what's going to happen in the future. And a really simple example is that when you stand up as a person, your heart has to pump harder to make sure you have enough blood pressure to do that. And in fact, if you look at people's heart rates, they go up before they start standing up. So your body is sort of thinking about, what is my heart going to need to do now so that in half a second I'm ready to be standing? And the robot's doing exactly the same thing. So it's thinking about how hard do I need to push with my right foot so that 1 second from now I'm not falling over.
My role in this project was to basically take the controller that we had before we started this manipulation effort and extend it so that explicitly thinks about the object that it's holding. So it has an explicit model of the object and its interaction with the robot. So we're interested in manipulating very heavy objects, so inertially significant in a sense, which means that actually thinking about the forces acting on the object and action equals minus reaction, the forces that the object exerts on the robot also becomes very important.
I think one of the hardest things about grabbing an object and moving it around with the robot is that it creates an entirely new set of problems of trying to decide where is this object that I'm manipulating and how is it moving. It's already hard for a robot to know where it is. So when we're trying to manipulate something like a plank, we have to just make pretty educated guesses about where is the plank, how fast is it moving, how do we need to move the arms to cause the plank to spin 180 degrees very quickly. And if we get those estimates wrong, we end up doing silly things and falling over.
So we're unable to read the encoder, the position encoder for our shoulder X, we call that. It's when the robot lifts its arm up like this. So we can't command it if it doesn't know where it's at. And sometimes sensors will break, cables will unplug. And so we're doing a really fast diagnosis to figure out what's happening. I am the electrical tech, Atlas's electrical doctor. And these other two folks here, Bill and Crystal, they're both partially electrical and very mechanical tech. So right now they're checking in on the wiring, and I'm watching to see if there's any signs of life as we go through and see if maybe we have a loose connection. Or maybe we have a dead sensor.
They use similar hydraulic systems in like a Formula One car, essentially. And they would, every event, they would take everything down and probably replace the seals, I'm assuming. And the difference is they know what the use case is. Where here, they're doing new things pretty much every time they run. They're trying new movements that might overextend an arm or a leg or collide with another part of the robot.
So everything Atlas does in the real world, we developed in simulation first. The simulator is sort of like a video game. It's a virtual world, and Atlas can run around in that world, and we can test a lot of variations of the behavior before we run it in the real world. It helps us understand the limits of what the robot can do. You know, can it jump even farther? Can it jump even higher? We can explore all of those questions in the simulator, and then we can test them on the real hardware. And often those tests in the real world will result in a broken robot, which is fine, we can fix it. But if we want to push the boundaries, we can do that in sim first.
Yeah, one of the main things I've worked on in this production, that's been the final jump. So we have a jump where it's doing a flip in the air. So previously we've done one axis flips. So we've done a back flip that goes only on one axis. And right now, this new jump, it spins around multiple axes. But one of the big challenges here has been that we're working at the very limit of the robot. So we've had to do a lot of changes to the controller. And basically we wouldn't have been able to do this kind of jump just 1 year ago.
This is the robot squeezing its limbs in the same way that a figure skater would tuck their arms in to spin faster. So it's actually trying to become as small as possible to spin really, really fast to get all the way around.
So the move you're seeing at the end we refer to internally as the sick trick. That's kind of our code name for it. I hope the world thinks it's as sick as we do.
It's a flip with a bunch of spins. I think it's something like an inverted 540. The robot is starting facing out, and then it spins, and when it lands, it's facing back at its takeoff box. It was a very cool move, and it took a lot of work to get that to land cleanly. It certainly inspires people to say, what if we could make a robot that can do this? And we can start exploring those questions first with Atlas. And if something seems to be working really well, or we see some application in it, we can develop that technology further and move it into our products that are actually going out and operating in the real world.
Well, the dream of humanoids is that they should be able to do all of the things that we do, right? A humanoid robot will be well suited for applications like manufacturing, factory work, construction, where a humanoid form factor actually fits very well with its bimanual nature, its ability to stand upright, move heavy things around, and work in spaces that were traditionally designed for humans to do work in.
I think what we're focusing right now for real world applications for this kind of robot, things like moving objects that are pretty heavy, especially in environments where it's either too dangerous for humans or where it's just generally something people don't want to be doing. I really want to see robots helping out in disaster response scenarios. I want to see robots moving around in the world in ways that allow humans to do things that are better and safer and happier with their lives.